Good evening, everyone. I'm here to record my next lecture on alkanes. This is a very short lecture of not more than 20 pages. So for this topic, what will be the focus? Okay, so basically we need to understand what alkanes are. They are hydrocarbons that only contain carbon and hydrogen. Okay, other hydrocarbons that we will cover include alkenes, alkynes, and arenes. So alkanes are considered saturated because we only see carbon-carbon and carbon-hydrogen single bonds, and there are no presence of any double or triple bonds. When we talk about unsaturated hydrocarbons, it will be alkenes and alkanes that contain double bond between the carbon atoms. Now, the open chain alkanes form a homologous series of saturated hydrocarbons with the general molecular formula CnH2n plus 2. So this is the general formula for all alkanes. Successive members differ in composition by one CH2 group. Each carbon atom in alkane molecule is a sp3 hybridized and has a tetrahedral molecular geometry around it. The bond angle is 109.5 degrees. Now, these are the first three members of the open chain alkanes, which include methane, ethane, and propane. Cycloalkanes are alkanes that contain one or more rings of carbon atoms. They are saturated hydrocarbons in which the carbon atoms are arranged to form rings. Cycloalkanes with only one ring have the general formula CnH2n identical to alkenes. So these are the members of the cycloalkanes homologous series. And these are the skeletal formula. And we notice that for cyclopropane, it is not so stable due to high angle strain. Straight chain alkanes have the IUPAC name as shown. Each member has a suffix A and E. We need to know how to draw the skeleton formula. It will be good that we know until at least the first 10 members. Okay? And here the other 11 to 20 members. Okay. The rules for naming branch chain alkanes are summarized in the table. Prefix, parent, and suffix, which we have already covered under the topic of introduction. So we should find the longest continuous chain of carbon atoms and use the name of this chain as the base name. Number each carbon atom in the longest chain beginning with the end nearest a substituent. Name the substituent attached to the longest chain as the alkyne group and give the location of each substituent by the number of the main chain carbon atom to which it is attached. An alkyne group is formed by removing a hydrogen atom from the alkane. The general formula for alkyne group will be CnH2n plus 1. To name the alkyne group, change the ANE to YL, methyl, ethyl, propyl, and butyl. And this is the difference between alkane and alkyne group in terms of the general formula. When two or more substituents are present, please list them in alphabetical order. When two or more of the same alkyne substituents are present, you can use the prefix di, tri, tetra, etc. to avoid naming the alkyne group repeatedly. Use comma to separate two numbers, use hyphen to separate a number and the words. This is something that we have already covered in the topic of Introduction to Organic Chem. Please refer to the previous video for more information. Now let's practice this. Skeleton formula, what is this? So to name this, first of all, we identify the longest continuous carbon chain, which is 1, 2, 3, 4, 5, 6, 7, 7. So it's something like heptane. And this is the one, so it's ethyl. Then we have methyl, so it's 3 ethyl, 5 methyl, methyl heptane. And E, the alphabetical comes first, so we name E before M. As for this one, it will be better if you draw out. If not, you can just directly do it. So the longest continuous chain will be 8. So it will be octane. And there are 1, 2, 3, 4 substituents. So in this case, we call it 5-ethyl 2,6-dimethyl here. So it's something like this one. This is a methyl, this is a ethyl, this is a methyl. So it's 5-ethyl 2,6-dimethyl. So put the ethyl first, although the order comes later. All right. Carbon atoms are also classified in terms of primary, secondary, tertiary, and quaternary, depending on the number of carbon atoms to which they are bonded to. So this is propane. So this is 2-methyl-propane. And this is 2,2,4-trimethyl-pentane. So the primary carbon is attached to only one carbon atom like these two. Okay. If it's a secondary carbon, is bonded to 2 carbon atoms. All right. If it's tertiary like this, it's bonded to 3 carbon atoms. So it follows like 1 carbon, 2 carbon, tertiary 3 carbon. Quaternary means there are 4 carbon atoms. That's how it's classified. As for hydrogen atoms, we also classify as primary, secondary, or tertiary, depending on the type of carbon atom to which they are bonded. So this hydrogen here is the primary hydrogen, is bonded to the C, that is bonded to one other carbon. So it depends on the carbon that's bonded to and how many carbon bonded to it. So if only one carbon bonded to this C, this is called primary. If it's having 2 carbon atoms bonded to this C, this is called secondary. 3, tertiary, that's it. So this carbon here, hydrogen here is considered one primary hydrogen. This is secondary because the carbon here is bonded to 2 carbon. And this is tertiary because this carbon bonded to 3 carbon. Constitutional or structural isomerism arises when there exist compounds with the same molecular formula but different structural formula. So from butane onwards, alkanes have constitutional isomers because of the branching of the hydrocarbon chains. These constitutional isomers can be either chain isomers or position isomers. Okay, so these are the examples. For butane, you can have another isomer called 2-methyl-propane. As for hexane, you have more isomers. So the longer the carbon chain, the more isomers it contains. 2-methyl-pentane, 3-methyl-pentane, then you can further do branching, 2,3-dimethyl-butane, 2,2-dimethyl-butane. Stereoisomerism arises when there exist compounds with the same molecular formula and structural formula, but differ in the way the atoms are arranged in space relative to one another. Enantiomerism is displayed when there is a chiral carbon center and there is a pair of enantiomers and which are non-superimposable in mirror image of one another, like 3-methyl-hexane, like this one. They are not imposable or superimposable, they are mirror image of each other. And the chiral carbon also take note there's no plane of symmetry. If not, cannot. All right. Also check for no plane of symmetry as well. All right. As for cis-trans isomerism, cycloalkane do display it because the ring structure, okay, restrict the free rotation of the bonds in the ring. So when we have this one, 1,2-dimethyl cyclopentane actually display cis-trans isomerism. So this is cis. And this is trans. The larger group is on the on opposite side of each other. Okay, one receding into the paper, one coming out from the paper. Right? Alkanes contain CC and CH bond. As the difference in electronegativity between C and H bonds are negligible, the CH bond is nonpolar and alkanes are nonpolar. So the intermolecular forces between the molecules are weak ID-ID attractions. So we can see from the data that with increased number of carbon atoms or increased molecular mass, the boiling point increases. This is because the number of electrons of the alkane molecules increases. The size of electron cloud increases, so the ease of polarization increases. Ease of polarization of the electron cloud increases. That strengthens ID-ID attractions or interactions, okay, which require more energy to overcome at a higher temperature. With increasing degree of branching, we notice that the boiling point decreases because when with more branching, the molecule becomes more spherical or more compact, and its surface area available for intermolecular interactions decreases. This reduces the extent of contact between neighboring molecules, resulting in weaker ID-ID forces that are overcome at lower temperature because of the decrease in surface area. Now, for the melting point of the alkane, you notice that it doesn't really fall on a very smooth curve. This is due to the effect of packing of molecules in a solid lattice. When the molecules are more closely packed in a solid lattice, the melting point is higher. Alkanes with an even number of carbon atoms are packed more closely in a crystalline state than those with an odd number of carbon atoms. As a result, the attractive force between the individual molecules are greater, and the melting points are higher for alkanes with an even number of carbon atoms. So you notice that the even number one are actually lower, okay? So the attractive force is actually greater. Yeah. Yeah, here, 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 here. So even number, the packing is better. Okay. So attractive force is greater. Solubility. Being non-polar, the alkanes are soluble in non-polar solvents such as benzene and are insoluble in water and other highly polar solvents. So some liquid alkanes are used in non-polar solvents. These liquid alkanes dissolve compounds of low polarity and do not dissolve compounds of high polarity. So because they are non-polar, they are insoluble in water and very soluble in non-polar solvents. So light attract light, okay? As well as you use a non-polar solvent to dissolve an alkanes that is a liquid at room temperature. As for density, the density of alkane will increase with increasing molecular mass, but will level off at around 0.8. So in general, alkanes are less dense than water. That's it you need to know. Let's move on to the reactions involving alkanes. So how do you prepare alkanes? Starting from alkenes. So we can actually use hydrogenation to react hydrogen with alkenes over nickel or platinum or palladium catalyst. Nickel is the least active and hence requires an elevated temperature and pressure, while platinum and palladium are more effective, requiring more ambient conditions, okay? Meaning it can be carried out at room temperature with these catalysts, just that these catalysts are more expensive to obtain. Now, alkynes which involve triple bond between carbon can also be reduced to alkanes under suitable conditions. Benzene can also be reduced to cycloalkane, all right, under suitable conditions as well. So there are other ways of preparing saturated hydrocarbons, either from alkene, alkyne, or you can prepare cycloalkane using benzene as well. Okay, this will not really be tested in the syllabus, so you just take a look at it. All right. This is another way to prepare alkane, but it's good that you observe and just take note of it. How is it done? All right. Another not in syllabus is this. This reaction involves the electrolysis of aqueous solution of the sodium salt of carboxylic acid using inert platinum electrode. And we have alkanes forming at the anode. So this is another way to prepare it. Just be familiar with it. All right. So these are the effects of the various reagents on alkane shown in the table. So we have sodium hydroxide, no effect. Hydrochloric acid, no effect. Even with concentrated sulfuric acid, no effect. Acidified potassium magnet, no effect. No decolorization. With air, no effect. Bromine, no effect. But it will decolorize in the presence of sunlight, where there's UV radiation. So you can see from the table that hexane is rather unreactive. Its behavior is typical of that of alkanes, which are unaffected by polar regions such as acid, alkaline dehydrating agents, or aqueous oxidizing agent. So this general lack of reactivity of alkanes towards polar regions can be attributed to this. Number one, alkanes are non-polar. So they consist of molecules which have no center of electrical charge. So they couldn't attract charged species like hydrogen ion, hydroxide ion, or MnO4 minus. They only contain non-polar CC bonds and are essentially non-polar CH bonds. So being non-polar makes them rather unreactive. They can also be attributed to it being unsaturated. So it's a saturated hydrocarbon. Unlike the unsaturated hydrocarbons, they do not have regions of high electron density. So they cannot attract electrophilic reagents or electrophile. They also do not contain any electron diffusion site to attract nucleophilic reagents. So cannot attract electrophile, cannot accept nucleophile, no way. The strong CC and CH bonds in alkanes do not break under normal conditions. So another consideration is the strong bond. In general, alkanes do not undergo reactions with non-polar reagents under the right conditions. They do undergo reactions, if you have sufficient energy for the reaction to occur. All right, so these are one example. So in order to calculate another alkane has this standard enthalpy change of combustion of -6780. So you need to predict where is it. So to do this, right, there's a way. Okay, so from this to the next one, if you count the difference in enthalpy change of combustion, it'll be around 660. All right. So from this one to the next one is about the difference of 2590. You divide by this is around 4. So you add another 4 more carbon to get this. So it's like inference. Alkanes burn readily in air or oxygen when ignited. The reaction is very exothermic, making alkanes an important source of fuel. In excess oxygen, alkane burn with a non-sooty flame, and it can be used as a test for saturated hydrocarbons, as unsaturated hydrocarbons will burn with a sooty flame. So given the same number of carbon, because of a higher percentage of carbon in alkenes, we'll expect to have more sooty flame, more incomplete combustion observed with alkene than alkanes. So for alkanes, for complete combustion, CO2H2 is produced. So this is something we learned under, I think, mole concept. So N plus, you need to take, this one is actually, because there's one O here, so when it comes to here, you need to take, because O2. So N here, so this is supposed to be 2N plus 2. So 2N plus 2 because there's only there's 2H here. So 1H here, so we divide by 2, you get N plus 1. So that's how they get this. And then this one is just N plus 2M plus 2. So this one is, you take the N plus N plus, because come to O2, you only have 2, so you times N plus 1, come to here, you do times 2 throughout. N plus total amount of oxygen is N. Oh, actually, there's another way of doing this. So instead of just, what they do is just 2N here plus N plus 1, then divide by 2 again, right? Another way is just take N plus, because it's 2 here, so you need to N plus 1 divide by 2. Oh, N plus 1. Correct. No? X. You know how this works? X plus Y over 2. It's Y over 2 here. So you take this again, then you become divided by 2. So actually should be n plus 1 divided by 2, then correct. Yeah, this is the correct. So when you move over to here, you divide by 2 because it's only O. So O2. So it becomes n 1 divided by 2, which is 3n plus 1 divided by 2. Yeah, that's how you get this. So you need to divide by 4 again because it's O2 here. So you divide by 1 over 2. You divide by 2 again. Okay. Incomplete combustion of alkanes lead to the formation of CO and C in addition to CO2 and H2O. So just take note that this is in addition, meaning there is still CO2 form, but there is some CO and C form as well. Okay, so you have other reactions going on. Cracking, again, is not really stated very clearly in the syllabus, but can be tested in synoptic questions. Cracking is the process in which large alkane molecules are being broken down into a mixture of smaller alkanes, small short-chain alkenes, and sometimes hydrogen. So the composition of the products depends on the condition under which cracking takes place. So yeah, long-chain alkanes is cracking form short-chain alkenes and hydrogen. We have thermal cracking and catalytic cracking. And what is their purpose? You can just read yourself. Halogenation, the next one to go through, of an alkane involves the substitution of one or more hydrogen atoms by halogen atoms. So the energy input in the form of heat or light is needed to initiate these halogenations. These reactions may be conducted in either liquid or gaseous phase, but not under aqueous condition because the water will react with any radical present. So the reagent for this reaction is Cl2 or Br2. Why not fluorine and why not iodine? I'll explain that later. The condition will be UV or sunlight or heat. Mechanism, you call it free radical substitution. Okay, so we will have the H substituted by the halogen. The focus will be more on chlorination and bromination because chlorination in the first place is very exothermic, so too dangerous to carry out. Iodination, because the overall reaction is actually endothermic and thermodynamically unfavorable because it's very because the bonds of I2 is weak, yeah, in general. Now, so this is one example. If we use chlorine, we'll observe the decolorization of greenish yellow chlorine and form white HCl fumes, which will turn blue litmus paper red because it is acidic. For bromine, we will see the decolorization of reddish brown bromine and the formation of white HBr, which will turn then blue litmus paper red because it's also acidic, similar to HCl. And this reaction always produces a mixture of products, chloromethane, and further substitution can occur if we have excess Cl2 present. Okay, to further substitute the H to form a mixture of different products. But for simplicity, we can just have this will do. All right. If we have Cl2 as limiting reagent, major product. Excess, major product, because we will be able to have all the H substituted by chlorine. So before we start the mechanism, we would like to introduce what is free radical. It's an atom or group of atoms that have unpaired electron, like all this. So free radicals are highly reactive, are intermediate in many of the reactions of alkanes. As they have equal number of protons and electrons, they are electrically neutral. The stability of the alkyne radical will depend on how many alkyne groups are there. So the most stable one will be the tertiary, because the alkyne groups are electron dominating. So they tend to stabilize the electron. Okay, they stabilize the unpaired electron. All right, so they will stabilize the alkyne radical as more alkyne groups are attached to the carbon. Okay, now we start with the concept of, now go through the mechanism. We start with the homolytic fission of the covalent bond, where the bond breaks in such a way that each of the atom acquires one of the bonding electrons to form the free radical. We call this homolytic because each one take one. All right. Then the curly arrow with the half ahead, which looks like fish food, represents the movement of one electron. How does free radical substitution occur? Now we have this. We have initiation, propagation, and termination. So during initiation, the chlorine is supplied with energy from UV light or heat to split into free radical via homolytic fission of the Cl-Cl bond. This involves bond breaking and will not proceed in the dark or at room temperature. It's easier to break the Cl-Cl bond than the CH bond or the CC bond because the bond energy is lower. In propagation, right, these steps involve both the bond breaking and bond formation. The major products are being formed in these steps. So in step 2A, we call this hydrogen extraction. The chlorine radical form will collide with the methane molecule, okay, and extract out the hydrogen atom from it, and thus forming HCl and a methyl radical. In step 2B, okay, the radical, the methyl radical itself will react with the chlorine and This is called the halogen extraction because it's removing the halogen from the chlorine molecule. So it forms chlorine radical. The chlorine-free radical product can proceed to attack another methane molecule, and the steps are repeated. So as a result, we have thousands of molecules of chloromethane formed by step 2A and 2B for every photon of light absorbed in step 1. So the reaction that occur, right, would be this, but we do not have this one, no. Because the formation of HCl bond is more exothermic than the formation of CCl bond. So hydrogen radical can never be formed. So if we want to have this reaction, then it means that you want the hydrogen radical to be formed. But the truth is, HCl bond is more exothermic. Okay? So it's actually easier to it's more difficult to separate this. That's what I can say. Yeah. So if this is the case, more isothermic means more stable. All right. So HCl bond is more stable. So you form HCl. So because more isothermy means more stable, so HCl is more likely to form. Okay. Then we come to the termination step, right? We have this one. So the Cl-Cl radical, it will collide and combine to form the stable product. Same for this one, and same for this one. Okay, so sometimes we have trace quantity of compound with at least twice the number of carbon atoms compared to the starting alkane. For example, we can form ethane from the methane. A chain reaction is a reaction that involves a series of steps, each of which generate a reactive species that brings about the next step. So we have a chain initiation step, followed by a chain propagation step, where each of which consume a reactive species and generate a new reactive species. And we have the terminating step in which the species are consumed but no longer generated. CH4 and Cl2 are present in large quantities. So once they are formed, the Cl radical and CH2 radical are more likely to collide and react with CH4 and Cl2 respectively, like in the propagation step, resulting in low concentration of the radicals because they quickly react to form. Now, this is one word example that you have this reaction. What are the reagents, the balance equation, how to write the name of mechanism, and the illustration of the mechanism like initiation, propagation, and termination. All right. You must write this. This is compulsory. You must show this as well. All right. So please take note of the arrow. We are looking out for that as well. There are more word examples. One more here. I will just maybe I look at this one first. Example 4. Methane reacts with bromine in the presence of UV light to produce CH2Br2. Write equation. Okay, equation. And this is the initiation, propagation, and further bromination by propagation step C and D, and C, D, C, D, something like that. So this reaction actually have a further bromination actually. After the CH3Br is formed, then you have more H substituted by Br. And termination. Right? For the next question, you have chlorination of propane in the presence of UV light to give a mixture of two monochlorinated products. Draw the displayed formula of these two products and suggest with a reason the expected ratio in which they may be formed. So you have product A. So expected this one, product B in the middle. To form A, because this is more likely the major one, because you can actually have 1, 2, 3, 4, 5, 6. You have 6 possible positions for chlorine. Okay. As for B, you only have 2. So based on probability factor will be 6:2, 3:1. So that's the answer. So when propane is chlorinated, the ratio of the two products formed differs significantly from the expected ratio. Why? The expected ratio is obtained by assuming that all the H atoms have the same reactivity. However, as a secondary alkyne radical is more stable than the primary alkyne radical, a secondary H atom is more easily abstracted, forming the more stable secondary alkyne radical intermediate than the primary hydrogen atom because of more electron donating groups. So since B is formed from the extraction of secondary hydrogen atom, while A is formed from extraction of primary hydrogen atom, can you tell? So this one is carbon here, is 2 carbon, so it's secondary. This carbon here is only 1 carbon, primary carbon, primary hydrogen. So ratio of B to B is higher than expected. Don't need to know how much, just higher. Okay, these are just your information that for your own, you learn from O level. I will not go through them. You can read yourself at your own time. The pollution problem, you can also read yourself. It's something that is learned at O level, so there's nothing new. All right. Catalytic converter was also covered, and other pollutants like carbon dioxide, how about greenhouse effect, and this term called enhanced greenhouse effect, okay, which is the correct term to be used. So enhanced greenhouse effect means it's only happening after the Industrial Revolution, where extra quantity of greenhouse gases are emitted, trapping more heat to enhance the natural greenhouse effect. Greenhouse effect itself is a natural, but enhanced greenhouse effect is due to man-made activities like burning of fossil fuels and more deforestations or industrial operations, okay, etc. And enhanced greenhouse effect is actually very detrimental, to the environment. Can read yourself, and sulfur dioxide and fuel gas desulfurization was all taught before. Lead compounds, then importance of petroleum as a finite resource. Why is it important to conserve them? How we recycle, the importance of recycling, Okay, just read yourself. This is a summary of alkane. Not much, because alkane is rather unreactive. So the chemistry of it is really very, very, very little. It's the least compared to other organic more compounds lah. Yeah, compared to alkenes in the next chapter. All right, so that's about it. I see you. I hope today's lesson you're able to understand. Any question, feel free to ask me. Thank you.